Hello everyone, and in this video today I want to talk about amplitude of noises a bit more. Then I will talk about multiplication and addition at the VOP level. Then I will talk about fit range relative to bounding box, and in the end I will talk about ramps. These three relative to bounding box, fit range and ramp, they are like connected together, so we will create something and we will use these three VOPs and the noises amplitude and addition and multiplication. We will use these three to create some noises in our geometry, and this time I will create the noises by this multiplication or addition. Last time we have used the addition and we have also used displacement along normals, but this time we will displace our geometry by the noise, but with this multiplication VOP node. I will start with our geometry. Let's create a sphere, polygon, and toggle this on. And we have our sphere converted to polygon, and frequency we can say 100. So we can have much more detail here. And let's connect our attribute VOP node. Dive inside this, and we have these two nodes, input and output. Okay, we have displaced the geometry by two ways, right? First, displacement along normals. We need our position and displacement. For amount, you can use a constant and connect this to amount and increase this. Wait, increase this. You would see your geometry points has been now displaced by this displacement along normal node, and we have this constant as an amount, right? So if we increase the value of the constant, and which is a float value, it only gives you the magnitude. So we are displacing our points in the direction of their normals, which is this is really like it is really dense now. So toggle this off. We can see our normals. When I connect this normal into the normal, we can see our normals. These are normals. You can see they are points normals, right? Okay, disconnect this. So we have already talked about these. We have like done this before, and there was another way. We have also used this way. What we were doing, we were adding the position and normal to displace our points. And how we did that? We created an add node, and in this add, first we were referencing sampling our point position values, point position vector components values, and these we can see here. We know each point, like we know the exact location of each point in the 3D space. And what we were doing, we were connecting our normal to this input value, and we were seeing this. And why it was like, why the points are being displaced when we connect the normal? Because now we are saying this: sample the points, like take the values of the points location and add normal with this, with those position. And normal is just a direction with a magnitude 1 because it's a unit vector, right? We have already covered that. And 1 unit, its magnitude, and we have direction plus magnitude from this normal port, and we are now adding it with the position. We knew this, right? Now what if I want to increase, like I want to displace these points by like 2 unit, not 1 unit, and 1 unit was the normal vector magnitude. And now we are displaying the points by 1 unit because the normal is giving us the value also. What if I want to displace this by 2 units? We can have a constant and we can input this into input 3 and then increase the value. Now we are displacing, but here I want to tell you something. When you connect this constant into this input 3, what it is doing, what it is doing. And in this video I want to talk about this and multiplication also. So let's say you have normal. Okay, you have normal, n represents, let's say, value. Okay, you have these normal location and its magnitude is 1, right? Now let's say something like this. Okay, now when you are adding a constant into this value, right, when you are adding a constant into this value, we can say n and plus 1 equals x and plus 1, x and plus 1, y plus 1, z plus 1. Okay, now when we are adding a constant 1, a constant float 1, right? So we are doing this to our normal, and what is happening here? The normal direction was x, y and z and its magnitude was like 1. Okay, the magnitude is changing like we wanted, right? So we wanted to displace our points, but not by 1 unit. We want to displace them by 2 units. So normal had 1 unit like magnitude, and now we are adding 1. So we are displacing, like we are changing the value of the like magnitude of that normal, right? But first, normal is a unit vector. Normal always like has a magnitude of 1. Second, when you are adding plus 1, we are changing the magnitude, yes, but we are also changing its direction. How? What if I say normal value is 0 in x, 1 in y and 0 again 0 in z? That means this normal is facing the y direction, right? Okay, now we are adding plus 1, so we are saying 0 plus 1, and here 1 plus 1, and z also we have 0 plus 1, and here the issue starts. So now the result would be 1, 2 and 1. Now this normal has changed its direction, right? Because now it says its direction is 1 in the x, 2 in the y and like 1 in the z. Now it is like pointing diagonally, and we wanted to have, like we wanted to displace our points along the normal, but we are now changing the normal direction. So when we add something to our normal, we are changing its direction. And here comes multiplication. I was adding this into the input 3 and normal in input 2. So now normal and this constant are now adding, which is giving us like different directions. So when I increase its value, we are displacing our points, but not in the normal direction. Not in the normal like direction. And what if I add this constant into this normal? Between this, like what if I add the value in this normal so I can displace this as we want? Let's say you have this multiply node, and when you multiply this normal and the end product is in this, and when you connect this constant to this input 2 port, now we are multiplying this value, this one constant value, into the normal value. Let's say you had this normal and now you are multiplying its value. That means you are saying that n multiply by 2. Now we would have the magnitude, which is now doubled. If we had magnitude 1, now we have magnitude 2 unit, right? But when we displace the points, normal direction stays the same and normal value stays the same. When you add the value to the normal, you are adding this constant into the input 2 in this direction, right? Not in the normal. You are not changing the normal magnitude, but you are like multiplying this constant to the normal. This constant now giving you the magnitude, the value, because it is multiplying with the normal one. And when you multiply anything, you get the same. When you multiply any number with 1, you get the same value, right? So this is defining now the value, like the magnitude of the normal magnitude will stay 1, because I can show you why. And when you add a constant, and constant value says you have 2, so you are saying double the normal. So this 2 is now acting as your magnitude, your value, but the normal is still acting as a direction. So when you are saying multiply this number into the normal, what you are doing now, and I can like show you, you are saying multiply n by 2 equals 0, 0 multiply 2, 1 multiply by 2, and 0 again multiply by 2, right? So what would be the result we would get? 0, 1 and 0. You see, we have still the same direction as we have before, right? So the direction is not changing when you multiply a constant with the normal, but its magnitude, now its magnitude is like changed, but its magnitude is changed, and that magnitude it is acting as the magnitude we want to like displace our points in the direction of the normal. And when you displace, let's say when you displace these points, the normal, let's say connect this first, this to this also, we can see our normals. These normals stays the same, and how you can see that our point has like the point has been displaced, but the normal stays the same, right? So this constant is now acting as the value we need to displace our points. If we are multiplying this constant value to the input 2, this constant is giving us the value, and this normal is giving us the direction we want to displace our points. Okay, and here I wanted to clear this concept, like adding and multiplying the normal with the constant value. And that's why we have our displacement along normals node, displacement along normals, and we are doing the same. This we are doing, we are adding and multiplying with a constant, and displacement along normals does the same. We have our position, the point position, and amount, like what amount we want to displace our points. So we already talked about this, the displacement node, and we have already talked about these, but I wanted to like have the difference cleared with multiplication and addition a constant into the normal. Okay, what if I want to have this value by some noise? Delete this and add noise. You can have turbulence noise, and we need like the position value sample, because we need to know like what point have which, like what noise value. We need to know like noise values at particular point, so we can add this value into our point, so we can displace it. I really talked, like the last video I guess was 40 minutes long, and I talked about the noise, right, in detail. So if you don't understand what I'm saying here, you can go and watch it. When I connect this noise value and let's say give this input, so now we are displacing our points by this noise value. And this noise value, this noise value, first we are sampling the noise value in this 3D space of each point at each point, and now we are adding this noise value into the input 2 so we can have this pattern. And we have already talked about the turbulence, attenuation, roughness, and amplitude. I want to share something here. We have alligator 1D noise, and this alligator 1D noise, okay, I will talk about it in a bit when we talk about ramps. So in the input 2 I want to add a constant, so you can add this constant. So now we are multiplying, this constant value into the noise values, and we are multiplying the normals, and normals is giving us the direction, and these two are giving us the value, like magnitude, how much you want to displace that point into this 3D space. And now we are adding this to the point values before, so we can displace it. Why do we need these points? Because we want to add these values at these position values that already exist. These points have position values, right? So when we are adding these values, so we can displace these points from here, not from 0, from here. So when I increase this value, first, when the constant is float, default is 0, float value is 0. Now when you multiply some value with 0, we get the input 0, output 0, right? So that's why we see nothing. And when we increase the value 1 to 1, now 1 is multiplying to this noise value and multiplying to normal, so we can have the direction. And when I say 2, now the noise is doubled. You can say 10, now we would see something like this. But if I deselect this, we can have only the noise up to here. We cannot increase it, but you can increase the noise more, the noise amplitude, like the noise amplitude, and you can say the noise value more by adding a constant into this multiply node, and you can have something like this. Roughness, you can have more detailed, like more hard edges. And from this example, I wanted to show you about this multiplication and addition at the VOP level, and I hope you understand what I am saying. And let's jump in the next part. And in this part, I want to talk about like fit range and bounding box sampling, and I want to talk about ramps. So let's create a grid. Okay, I have already created some notes for you about this. So I have here, I have already created some notes, but we will jump onto these later. But first, I need to explain these concepts. So we have this grid, okay, and let's create first. Okay, we have this grid. Let's create a box also. Okay, we have this box. Now copy this box to these points, grid points, and we have this. You can decrease the box size. Okay, now we have something like this, right? And what decides the scale of this when you are copying, like when you are instancing these boxes onto these grid points? So what defines the pscale value, the point scale value of these boxes? And they are defined by the pscale attribute, which is not here right now, but that's why we see these pscale values default to 1, because now the pscale attribute does not exist on these points. That's why we are seeing all the boxes similar, and the value of these boxes are equal to this, the scale value. So what if in the last video I talked about the pscale attribute, right? what if now I want to, what if I want to, we will do the same. We will do the same. What if I want to change the sizes of these boxes? And in the last video we did something like we created a bind export, and we created a constant or noise, let's say turbulent noise, and we sampled the noise values and we input that noise to the bind, and we, let's say, p scale. And when I go here, we can see our p scale values coming from this noise and going into the p scale attribute, and now this p scale attribute is defining the scale of these instances, right? Okay, now in this part, delete this. In this part I want to share something. First we will talk about the bounding box. And what is like bounding box? We have this grid, right? And bounding box is a rectangular box. You can say it is a rectangular box, and it is like the minimum rectangular box, and inside that box the geometry is like tightly fitted. We can say what is the minimum rectangular box, which is the what is the smallest rectangular box we can fit this geometry inside. So if we have a geometry, a rectangular box, it is invisible now, but there you can see we have like this bounding box. When you say like shaded, this is our rectangular box for this geometry. But if you really want to see, let's create our test geometry, let's say rubber toy, and turn this on. Now this is our bounding box. This is our bounding box, and it is the smallest box you can create to fit this geometry inside, right? And when you see here, we have this. So first we would reference our bounding box. Inside this we have a node relative to bounding box. Connect this P to the P and this to CD. Now I want to tell you really important thing here. This node calls relative to bounding box. We have this grid, and we have a bounding box, the smallest bounding box we can fit the geometry in, right? And this bounding box and this relative to bounding box node, VOP node, what it do? It gives the geometry a value, like it normalize the point position component values, and it changes the value from 0 to 1. So when I connected this, we see now the position values are going into this relative to bounding box, and now this relative to bounding box changing the values of the components, which is x, y and z, and it is converting those values into from 0 to 1. So now the values would be from 0 to 1. Let's open our geometry spreadsheet. You see our values are between 0 to 1. 0 to 1. I have created the knot. You can see here. Where is the knot? You can see here. First, bounding box. Smallest 3D rectangular box that completely encloses your geometry, right? The box that can cover your geometry. And relative to bounding box, it takes the point position P, looks at the geo bounding box minimum and maximum, convert that position into a value from 0 to 1 for each axis. Let's read it again. Looks at the geo bounding box. This is our geo. It has a bounding box, right? It has a bounding box and looks at the geo bounding box minimum and maximum and convert that position into a value from between 0 to 1 for each axis. Let me explain this so you can understand this better. We have this bounding box and this bounding box has values. What if now we have the vector coming out from this bounding box because it is converting the value of each vector component to 0 to 1, from 0 to 1. You can see it here. We have our C, R, G and B, which was X, Y and Z because we were referencing our position, right? And we are giving this a value and I have outputted this into the CD. That's why we are seeing these into the CD. And now you can see our values before was minus 5.0, now it is 0. It was 3.888 and now it is 1, 2, 3, 4 and it is the values between 0 to 1. And we have three values, that's why we are seeing colors. But what if I convert this vector into each float value? So we can say vector to float. And when I connect this, now we are seeing gradient, but it is from white to black. Okay, now you understand it, what I mean. This relative to bounding box is converting each component, each vector component value from like in between 0 to 1, from this range 0 to 1. And it is doing for each component the X, Y and Z. So now we are like outputting only the X value. So I want to see what it is doing to the X value. And when you open the geometry spreadsheet, now we would see, connect this CD and disconnect this. Let's say bind export, connect this into this input and we are in the float type right now. That's why we were seeing this CD value, and when I convert this into the vector and when I override type input, because we had input CD here and we are now overriding this input to this CD, that's why we are seeing 3. Let's delete this and delete this, connect this to CD and now we have 3 because this is a vector and vector has 3 values. It can has 2, 4 but in general it has 3 values, so that's why we are seeing R, G and B and all these values are same. When I go into the scene tab and you see here we have the values of these points from 0 to 1. 0 means black, 1 means white, because R, G and B, 0 means black and 1 means white. That's why we are seeing this. So this vector, this reference to bounded, that this relative to bounding box is like converting the values that are coming from this into in the range from 0 to 1. And now we are like separating this vector into its particular X, Y and Z component values, and we are now outputting this values into the CD so we can have this value as our CD, right? And here how the relative to bounding box work, it converts the value, inputting value into in the range between 0 to 1. And let's say I want this value that is coming from this vector and I want this value in the pscale value as a pscale value, so we can have a bind export, and in this bind export we are using float, so we would have one pscale value because pscale works with float. When I input this and when I say pscale, now we have this pscale value at each point. When I'm copying these boxes onto 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 each point, and each point has its pscale value, which is in between 0 to 1, right? These values coming from 0 to 1, inputting the value, then it is converting those value. And how it is converting those value? It is normalizing those values. And how it is normalizing that? For example, you have the value coming from this into this is, um, let's say you have a value 2. Okay, the value coming from this into this p 2, and 2 is for x vector component, the value is 2. And now I want this 2 value, and the range before was, let's say, 1 to 10, right? 1 to 10. And now the input value for that x vector component was 2. So now this is like normalizing this value into this range 0 to 1. Before the value was 2, now it need to fit that value from 0 to 1 as the same, like the value should be the same but in this range. So when you see 2 is at the 20% of 1 and 10, and zero point 0.2 is at the same 20% from 0 to 1, right? So that's how it is normalizing the value. And normalization of vector and normalizing these values are different. Normalizing the vector is like it don't it doesn't do anything, like it don't change the normal direction, but it changes the magnitude to 1. That's how we normalize the vector, right? And and it is now like changing the value, and we have these p scale values. And you can see when I connect this into the cd also, and now cd also has the same value as this. We are seeing this is 0, this is 1, and all these box p scale values exist from 0 to 1. They are in this range 0 to 1. And what can I do? I can give this a ramp. Ramp is a graph that changes the value from 0 to 1. It is reading the value from 0 to 1, and it changes into a new value. I will say it again. Ramp is a graph that changes 0 to 1 value into a different number. And I will show you how. Let's give this a ramp. Now we have this ramp VOP node, and you see it is yellow. And why this is yellow? Because this node is being promoted to the geometry level, and you can see our ramp here. When you give this name something like ramp tut, because it is a tutorial, so when you go at the geometry level, you see our ramp tut is here. That's why it is yellow. And I have already talked about promoting a port, promoting like something like this input. I have already talked about promoting this input at the geometry level, and it's very easy. Just middle mouse click and promote parameter. That's how you can promote something. And now this is being promoted at the geometry level, and we can see our ramp here. You see this ramp is showing us some colors because this is a color ramp. This is a color RGB color ramp, and there are two types of ramp you can see here. We have spline ramp float, and we have RGB color ramp. And what is the difference in between? The RGB color ramp inputs a float value, a single float value, and it outputs a vector R, G, and P. And our spline ramp inputs a float value and gives output a float value. So let's say I don't want RGB color right now, so I want a float value because we are outputting this into the p scale, and p scale need one value, not a vector. So in this ramp, when you go at the geometry level, you see now the ramp is inputting our 0 and 1 value. that exist on this geometry. These points have 0 and these points have 1. All these points are between 0 to 1 because they are the value coming from this float value 1, which is the x value, x vector component value. And you can see here we have r, right? We have p scale 0 and we have r. R is from 0 to 1. R is the value which is going here, and it is from 0 to 1 as same as the p scale value. Why the p scale is 0? Because the ramp, because of this ramp, because when you go here you see our both values are 0. So when you toggle the display on, you see nothing because these two values are 0. Ramp is like inputting those values from 1 to 0. So when you increase this value, you are seeing this, and this is our 1. This is our 1 value, and this is our 0. You can create more points, and you can like manipulate this ramp. You can create a shape with this ramp, and you can like change their position. So when I delete this and delete this, now I have this 1 value at this position. You can change the value position, right, with this ramp. So let's increase the size of this, let's say in the Z direction, and we have something like this. Go here inside this, we are using, okay, now this ramp, when I give this something like this, you are manipulating the geometry, right? You can increase and decrease. You see the value is really, and when it's 0 they are like disappeared because they have p scale value 0, because the output is going into the p scale, and when p scale is 0, that means the scale of that object is 0. Now I want to tell you about the Fit Range VOP node. Let's create a Fit Range node first. Fit Range, and Fit Range is like it says. Fit Range does what it says. It fit a different range into the range you provide this node. So the output value that are coming from this output, or say this x float value 1, which is x vector component, right? The value that is coming into the fit is from 0 to 1, right? Because of this related to the bounding box node, right? The value is converted, the value is normalized by this into 0 to 1 range, and it is going here and here and here. So now fit range source minimum. So the value that are coming from this node like exist in which range? It exists from 0 to 1, right? The ramp only works with the value 0 to 1. It knows two numbers, 0 and 1, and everything inside that it can change it. Like it have the power to change them. You can change that from here. So inside this node, we are inputting this node a value from 0 to 1, because when you go here, you have p scale value from 0 to 1, right? And now we are inputting this from 0 to 1, and now this, with this fit range, you can like have the control over the output. The values coming from this node are in the range from 0 to 1. We can say I want the same value but in different range. Let's say you want the value coming from this node. I want this value from 2 to, let's say, 4. The values would be same, but they are now in a different range. And why do we need it? Let's say, I will give you one example. I have created the nodes, right? But we will see them later. But let's create an example. Let's create a noise, turbulent noise. Okay. Sample the position first, then this noise, put this value into the input of this bind pscale node. So now the value that is coming from this noise, they are going into this, right? And the values are from, we don't know, but yes, we know this is 1D alligator noise. I have already talked about 1D, which would give like a single value to each of the vector component, which is x, y, and z. So it will give the same value, and if we have 3 noise, it will give different values to like to these 3 vector components. We have this amplitude, and I said that I will talk about amplitude a bit more. And amplitude, as I have talked about, that the number is in the range between -1 to 1, but no, you can understand that too. You can understand the amplitude with that thinking too. But the alligator noise, if you want to understand this amplitude in a deeper level, you need to know about what is the input value, what is the range of this value, and we are using alligator noise, which gives, you can see it, which gives us the value from 0 to 0.5. So now the value that is coming here is 0 to 0.5. When you see this, you see the value is from 0 to 0.5. It's not more than 0.5 and it's not less than 0. So this noise is giving us a value from 0 to 0.5, and we have amplitude, which is 1. Amplitude 1 means that the range of the values would be from 0 to 0.5 exact. Like strength would be, the strength would be 100%. So the values that are coming are with, like, they would be from 0 to 0.5. And when I'm saying amplitude is 0, so now the values that are coming from that noise would be 0.5. So they would be half. They would be 50%. Amplitude is saying 100%, 50%, 25%. We have 0, 25%. You can go in the minus also. When you're saying amplitude is 0, now the value that are coming from that would be multiplying by 0. So now we would have nothing. The values that multiply 0, we have nothing. So this is what amplitude do. You can say that amplitude is like -1 to like 0, -1 to +1, -5 to +5. But no, amplitude is like, I can say attenuation. Attenuation also is something like the strength of the noise layers on top of each other. Amplitude says that the noise that are coming from the noise type, right? The noise is coming from will go through me, and I will tell like how strong that noise would be. And now we are saying 50.5, that means 50% of the strength, 100%, 100%. You can like understand this amplitude by like 150% like this, so we can have better understanding of this. I'm saying amplitude 1 noise, you can increase the roughness, so we can have like sharp values, exact, like how can I say, the difference in these values would be large, like to the point values. Okay, why do we need this fit node? Because the values, let's say you want, the values are in minus right now, so now the faces are inverted. What if I want a noise value for a pscale, for an attribute pscale, because you want to scale some geometry instances in your 3D scene, and you want to scale them in positive. But if the noise is coming from is in minus, then how would you like convert it? That's how we have this fit range VOP node. You can like change the noise that is coming from this into different range. I'm saying the value that is coming from our source is from 0 to 0.5. The source is giving us values from 0 to 0.5, and now we are saying that the output minimum value, if the source is sending us zero point 0.2, if the source is sending us zero point 0.2 value, but we want to have minimum of one scale value, because to scale something we need some value, right? And minimum, how small you can go, it's up to you. But I'm saying I want to have the like exact same value as the original geometry has, because I want to scale after that. Okay, so it is saying if the value is 0.5, then if the output would be 0.5, then the geometry would be half in scale. But I'm saying the input is from 0 to 0.5, but I want the output from 1 to 2. So now we are scaling these according to the input by the output by these two. So we were in this range first. Let's say we were from 0 to 0.5. We were in this range. Right? Now we are in this range. We are in this range. But let's say 0.5, the value is 0.25. It is inputting us a value 0.25, and what this value would represent in this 1 and 2 range, half of 1 and 2 range, which is 1.5, right? 1.5. This is the 50% of this, and this is also the 50% of this. So we are changing these values into a different range, but the proportion of these values are same, the proportion. And fit range is really important, because if you want to scale something, we cannot have something in minus, then the geometry would be scaled in negative, right? There can be so many instances where you don't need the values in minus, so we can have our fit range, so we can use it to like convert the values coming from a different range to another range, right? And I guess we have completed this video, and let's check our notes. First, relative to bounding box, it takes a point position P, looks at the geo bounding box minimum maximum, and convert that position into a value between 0 to 1 for each axis x, y, and z. So it is giving a value from 0 to 1 for each axis, each vector component, right? Bounding box, okay. And let's take a look about fit range. We have just talked about it, so let's talk about it again. Fit range takes a value from one range and converts into another range, like we did 0 to 0.5, and we converted it into another range from 1 to 2. You have a noise value 0 to range in between 1 to +1. To convert it, fit inside the range from 0 to 10, it would be 6, because 0.2 is 60%. So it is like referencing its percentage, like 0 to 1, 0.6 would be equal to 6 in the range from 1 to 10, right? 60%. Okay, so 60% from 0 to 10 would be 6. Okay, spline ramp, input single float value, output single float value. RGB ramp inputs a float value and converts a 3 vector RGB. Ramps only work ranging from values from 0 to 1. Example, source minimum, source maximum. It is like what is the range, the input range, and this is the output range. right? Fit range coming out. You can screenshot this if you want. We have the built-in natural noise. Oh, this is from the last video, and I guess if amplitude, it talks about amplitude also. I have created this also, but this is from last video, I guess. Okay, okay, this is also from the last video. So I will have another video about this VOP, then we will jump into our vex vector expression. We were creating our vector vex language by nodes. So it's same as vex, but in the next after in the video after after the next video, I would start the vex also. So I will see you in the last video of VOP, I guess, and which would be tomorrow. So until then, take care, and that's it for this video.